Hello there, and in this video we're going to continue our discussion of linear regression and some applications and interpretations that one can get from it. So let's consider the temperature and number of ice cream sales on a beach example that we discussed in the last video, where we saw that there was an apparent positive trend between temperature and number of sales. Yes, there is a strong correlation that we realized, but that does not necessarily imply a causational effect. So some applications that you can get from linear regression is via the line of best fit. So let's calculate that right quick for our data. So the covariance between x and y, here I'm referring to x as temperature and y as sales. Again, you can find this to be equal to 14.67. And let us also calculate the variance of x, and that's going to be about equal to 8.92. So recall from these two values, we can find the slope of the line of best fit to be equal to the covariance between x and y divided by the variance of x. And you'll see that this is equal to 1.645, which implies that the slope of the line of best fit is going to be going upwards. You can also find that the y value, or the y average and the x average, are going to be equal to 82.75 and 48. So from these two, you can calculate the line of best fit vertical intercept to be equal to y bar minus m times x bar. So the y-intercept, or the vertical intercept, is going to be negative 88.11. So these are our two line of best fit statistics. Alright, so that means what? So that means the line of best fit is equal to y hat is equal to 1.645 x minus 88.11. So this is the line of best fit. So if we look at our values here, so values, and I've scattered these not correlated to our data, but nonetheless you have some picture that is similar to this. So remember, y hat is an approximation to y. So of course this line is not going to pass through all of the points. There is going to be some distance between our approximations at our x values and the approximations of our y values. So this distance between our line of best fit and our actual values are called residuals. Residuals. So the residual are the distances from y to y hat. And some people define it to be the residual of x to be equal to y minus y hat for a particular x value. Alright, so if that is true, then let's calculate our residuals. So we have our x values and our y values already calculated. So it's going to be 79, 82, 84, 86. Our y values were 42, 46, 51, and 53. So let's calculate our y hat, our approximations to y values. So I'm going to take all these values x, so 79, 82, 84, 86, and I'm going to plug them into my line of best fit. So for this first one, this is going to be equal to 1.645 multiplied by 79 minus 88.11. This next value is going to be 1.645 times 82 minus 88.11. 1.645 times 84 minus 88.11, and 1.645 times 86 minus 88.11. So this is the approximation that our model gives to the value of y. And you'll realize that this is going to come out to 41.83, 46.77, 50.06, and 53.35. So these are our y hat values. And notice that these values of y and y hat should be relatively close to each other because this line is the line of best fit. So it should be technically close to each other. So the residuals of our particular x values is the distance between our values of y and our y hat. So this is going to be y minus y hat by definition. So this first one is going to be equal to 42 minus 41.83, 46 minus 46.77, 51 minus 50.06, and 53 minus 53.35. So once you do these calculations out, and Excel is very useful at these types of calculations, you'll get 0.17, negative 0.77, 0.94, and negative 0.35. Alright, great. So what does these say? So that means the distances between all of our approximations are about less than 1. Alright, so there's another calculation that pretty much measures the total distance across all of our points, and that's what we call the sum of squared residuals, which some people usually abbreviate by SSR. So the SSR is defined to be equal to the sum of the differences between y and y hat squared. So based on this picture, this is going to be equal to 0.17 squared plus negative 0.77 squared plus 0.94 squared plus negative 0.35 squared. So that means we're going to get the SSR equal to 1.63. And one property of the SSR is that if your r squared value is approximately equal to 1, then your SSR value is going to be approximately equal to 0. Remember, r squared equals 1 implies a perfect linear correlation, which means the distance between our y values and our approximation should be 0 or something extremely close to it. Alright, so a couple things that some people usually get backwards here is this residual actually an error in our calculation? So is there a relationship between residual and error? And it's important to know the difference between these two. So remember, residual is the difference between observed and predicted values, whereas error is observed and true values. And usually we do not know the true values here. So remember, the predicted values is usually, the goal of it is to pretty much, guess what the true values should be. And of course, the observed values could have some error associated to them as well. We don't necessarily know. So of course, that is pretty much the difference between residuals and errors. But of course, in this video, we pretty much focused on, what is a residual? It's the difference between the y values and the predicted y values, y hat. So yes, recall the residual for x is equal to the difference between y and y hat. And the sum of the square residuals, SSR, is going to be equal to the sum of those squared differences. And of course, remember the difference between residual and error. Residual is the difference between observed and predicted, and error is the difference between observed and true values. And that's pretty much an overview of errors and residuals.